Now let us move on to the effect of turbulence on premixed and non-premixed flames. We will look at the general features first and then move on to specific aspects. So we have two different flame types, and premixed and non-premixed, and within each category the flame can either be laminar or turbulent. Okay. We know how to deal with laminar premixed flames. These days it is even easy to compute the structure of unstrained and strained laminar premixed flames with detailed chemistry and the full multi-component diffusion. And for laminar non-premixed flames also the calculations can be done by starting with the mixture fraction approach and creating what are called flamelet libraries with detailed chemistry and transport properties. Okay. But when it comes to the effect of turbulence on the premixed and non-premixed flames, we have one of these three approaches. See, turbulence, remember, is flow in which the flow and other scalars fluctuate, and they fluctuate in a very specific way, that the spectrum of the fluctuation should generally have a continuous behavior with a certain power law. Okay. Otherwise it is just white noise does not constitute a turbulent flow, or flows with discrete modes are also not turbulent flows, they are just unsteady laminar flows. Turbulent flow has a very specific definition, this was discussed earlier, and therefore there are three approaches to modeling turbulent flames. One is to look at only the mean field. It is called the Reynolds average Navier-Stokes approach, where what we solve for is only the mean value of a particular quantity, that is shown as a simple horizontal line here. Imagine temperature or velocity or one of these variables. What is solved for is only the average value. Okay. But in reality it may have fluctuations of different frequencies and different length scales as shown in the same plot. Okay. And the next level of detail is detailed simulation is large eddy simulations, where what is captured is just easier to explain here. So the RANs, you get only this. Okay. In LES you recover some of the large scale behavior. This is what you will get in LES. Okay. And so you have RANs is only average stationary behavior is captured. LES is large eddy simulations, large scale fluctuations are captured, and DNS. So direct numerical simulation, all scales are resolved. A DNS simulation for a variable like this would look like this. There will be several other frequencies. I think you get the broad idea. It will capture the large scale motion as well as the intermediate scale and all the way down to the smallest possible scale, which is the Kolmogorov scale. Okay. So these are the three approaches that are used. What is commonly used in practice is, or what can be done with the computational resources that are normally available, is a RANs simulation. Slowly industries are moving towards LES simulations. DNS remains as an academic activity. Okay. I thought this poem by Lewis Richardson, who was a meteorologist, captures the essence of turbulence. This he wrote to bring out the message that a turbulent flow has a spectrum of length and time scales with energy exchange between different scales. Okay. So big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So now let us look at a simple way to actually understand what is the range of scales that are present in turbulent flows. So the largest scale will have a dimension that is approximately the length scale that is of relevance to the problem. In the case of a liquid rocket motor, it could be the injector diameter, and in a gas turbine it could be the length scale associated with the injectors or the liners or one of these macroscopic features of the geometry, and the smallest scale is where the viscous dissipation becomes significant. Okay. So the energy contained in an eddy of size L is U dash squared. Okay, it is the kinetic energy that is contained in the eddy, and it has a turnover time of L over U dash. Okay, so an eddy of size L with a velocity U dash will have approximately energy contained in this eddy is the kinetic energy, which is U dash squared by 2. We are going to do a scaling analysis, I am going to leave out the 2, divided by the time. This is the energy is U dash squared, and the energy transfer rate is U dash squared by the turnover time for the eddy, which is L by U dash, which is equal to U dash cube by L. This is the rate of transfer of energy from the largest eddy to the next size eddy. Okay. And this energy transfer will happen, remember Richardson's poem that the smaller eddies feed on the energy of the larger eddy, and in these larger eddies the role of viscosity is negligible. Viscosity becomes important only if you go to smaller scales. Okay. So this is the energy transfer rate from the large eddy towards the smaller sizes, and this energy transfer will happen up to a point, okay, up to a point beyond which viscosity takes over. Okay. And when viscosity takes over, the inertial effects and the viscous effects are comparable, and therefore the Reynolds number at the smallest scale will be of the order of 1, because that is when viscous dissipation can become significant. Until that point, inertial forces will dominate, and therefore this smallest scale is defined by the condition that the Reynolds number at that scale should be about 1. Okay. And by combining these two equations, you can get an idea of what is the spectrum of scales, and that is what I have summarized here. The rate of transfer of energy from the largest eddy towards the smaller sizes is U dash cube by L. It will go all the way up to a certain scale, and then at that scale it will get dissipated by viscosity. Okay. And you can rearrange this equation to show that the size of the largest eddy, the ratio of the size of the largest eddy to the smallest eddy will be proportional to the Reynolds number raised to 3 by 4 power. Therefore, larger the Reynolds number, larger is the separation of scales. Okay. So similarly, you can show for time scales also that the time scales will depend on the Reynolds number of the flow. So larger the Reynolds number, larger is the separation of the scales. So scales range from size of the device to a few microns depending on the Reynolds number. Reynolds number of the order of 1 is where viscous dissipation will dominate and can significantly convert the kinetic energy contained in the eddies into heat. When the Reynolds numbers are large, viscous effects, the Reynolds number is a ratio of inertial forces to viscous forces. So when the Reynolds numbers are large, the inertial forces dominate, the amount of energy that is dissipated by the viscous forces is negligible. Only when Reynolds number becomes of order 1, viscous forces will dominate.
Like viscosity is some physical parameter that is essentially popping out because of non-equilibrium in the flow. So the moment you have a different non-equilibrium happening between two layers of fluid, then when you say viscosity pops up. The moment you say Reynolds number comes into picture of 1,
Yeah.
then the viscosity has no role.
Not really actually. It is when Reynolds number becomes 1 that the viscous forces dominate. A state of active non-equilibrium is maintained. This is I would like to construct an analogy with the flame example that we discussed earlier. So you have a conical flame, and the temperature at the flame is different from the temperature away from the flame. For example, in the reactant side the temperature is lower, on the flame the temperature is higher. So there is a gradient in temperature. This gradient in temperature is maintained by continuous supply of reactants to the flame. If you stop that, the gradient disappears. In fact, everywhere the temperature becomes the same. Similarly, in a turbulent flow, you are adding energy by the kinetic energy that is provided to the largest scales. For example, imagine a fuel injector like the one that you use in liquid propellant rockets. Let us say 10 millimeters in diameter, and liquid hydrogen or gaseous hydrogen is coming in with 100 meters per second. That contains a certain kinetic energy associated with the length scale of the diameter of the injector. And now this energy cascades through smaller and smaller scales. As to how the smaller scales are produced itself is an interesting topic. It is produced by vortex stretching. So the energy gets transferred from the larger scale till a point where viscosity will convert this kinetic energy into heat. In fact, viscosity has no role in the side of the larger scales, because Reynolds numbers are very large. The inertial forces are much higher than the viscous forces. Once you reach a length scale that is much smaller, for gradients to actually dissipate away the heat, the Reynolds number must be 1. Viscosity dominates when Reynolds number is 1. When Reynolds number is large, viscosity has marginal role.
I have included like rho Vd is nothing but delta V, that's what I am thinking. No,
it's not delta V.
It's not delta V.
It is the length scale of that AD. Yeah.
So then this is objectively the picture.
Correct. Yeah. Any other questions? No. The reason why I wanted to derive the relationship between the large scale and the small scale is to look at mixing rates or estimate a time scale for mixing. Okay. So a typical time scale for mixing is length divided by velocity. So we can calculate mixing time scale for the largest scale and for the Kolmogorov scale, okay, which is what I have done here. You can so kappa of L will be L over U dash, and you can express that in terms of the dissipation rate and the kinetic energy of turbulence epsilon by K. I am using this because this is what you typically use when you are doing calculations with RANS models. K epsilon model. Okay, the epsilon is the dissipation rate. Remember that it is U dash cube by L, and K is the intensity of turbulence, which is U dash squared. Okay, so the stretching rate or the inverse of the stretching rate at the integral scale or the largest scale is epsilon by K, and you can similarly calculate the stretching rate at the Kolmogorov scale, which will be eta K divided by UK. We have derived expressions for both of this in the previous slide. If you take the ratio of these two, it will be proportional to the square root of the Reynolds number. Therefore, there are two conclusions. One is that mixing rates are much higher at the smaller scales, okay, and larger the Reynolds numbers, this disparity will, separation of scales will be wider and wider, okay. So molecular mixing is dominant at Kolmogorov scales, and remember that molecular mixing is required for chemical reactions to happen. It is not just sufficient to bring a bulk of fuel in contact with bulk of the oxidizer. It is important to mix them thoroughly for all the fuel and oxidizer to react, okay. So this is quantified by what is called the scalar dissipation rate, which is chi equals 2d grad z squared, and this is proportional to epsilon by K. So turbulence, therefore, remember that in a premix situation mixing has already happened, so that the mixing rates are very different at integral scales compared to the mixing rates at Kolmogorov scales will have marginal effects on the dynamics of premixed flame. But on the other hand, if you look at non-premixed flames, that molecular mixing is significant at Kolmogorov scales, and that there is marginal mixing at integral scales, means that there will not be any reactions at integral scales. The reactions happen because of mixing at the flame structure is dependent on mixing at the Kolmogorov scales. Okay.
This psi equals to 2d
Yeah,
times the
that,
gradient of species concentration.
yeah, I did not, I missed that part. I just want to go back to, this comes from the conserved scalar equation, where we showed that, I am sorry I missed that. You remember this equation? So, we showed that a conserved scalar will satisfy a convection diffusion equation. Therefore, rho u d beta dx minus rho d d square beta dx square is equal to 0. That is what we showed for a conserved scalar. So, the first term on the left hand side will be 0. So, the reaction rate under purely mixing control situation is equal to negative rho d d beta dx squared d square y by d beta square I. So, omega dot I is negative rho d d square beta, let me not use beta, I will use the normalized scalar which is z, keep making too many mistakes, sorry. I think this is correct, okay. So, this is for a 1D case, right. If I generalize it to 3 dimensions, this is dz by dx dot dz by dx, it is actually the gradient of z dot the gradient of z. In 1 dimensions, it is simply dz by dx squared. This is for 3D. This, by the way, is called the flamelet equation. Okay. From here you can identify a quantity called chi, which is 2d grad z. This is a very important quantity. Remember that unlike a premixed flame, if I have a premixed flame, I had no difficulty, we had no difficulty in assigning a thickness to it, and it had a characteristic speed which is SU0. Once I have a length scale and a velocity scale, I can define a time scale as delta over SU0, okay, which we also showed depends on the reaction rate, okay. So, we could, in a straightforward way, we could connect the time scale of the flame to the reaction rate, but diffusion flames are tricky because the reaction rate is limited by the mixing rate, and the mixing itself is dependent on the flow, and when the flow conditions change, the structure of the diffusion flame will change, the reaction rate will change, and therefore the time scale for mixing is different for different flows. So, it is not easy to find an intrinsic length and velocity scale for a diffusion flame. The convenient scale is this. As you can see, this has dimensions of 1 over seconds, okay, and this is the mixing rate, and a convenient time scale is for a diffusion flame is 1 over chi, okay, and the length scale is d over chi. Let me write clearly, always remember this. Length scale is length scale in a diffusive situation is square root dt, which in this case will be d over chi. But there is no universal value of the scalar dissipation rate for diffusion flame, it depends on the flow conditions, therefore it is different under different conditions, okay. This is the scalar dissipation rate.
This essentially talks about the diffusion of the species from one space to another spatial location.
Yes,
Where
the rate of mixing, the rate of diffusion, yeah.
Okay, but where we have not talked about flow interaction with the diffusion rates.
The Z is governed by this equation. I keep pressing the. Z as a function of x, remember, is controlled by or is governed by convection diffusion balance without a source term, and the flow effect comes through this equation. So from here we will get a Z as a function of x, which will give us grad Z squared. Therefore the mixing rate is in fact intimately connected to the flow, connected to the flow, yeah, and the mixing of the flow. Any other questions? This distinction between premixed and diffusion flames is important. This is the premixed situation, this is the non-premixed. Yeah.
Lewis number is not equal to 1.
Yeah.
How do you do it?
It's too bad actually. This well, okay, what I meant by that is that the mathematics is not as nice as this, but the simplest way to deal with that is you define one more scalar, okay. So when the number of variables for which the diffusivities or the transport coefficient, if you are forced to choose different values for you may be interested in a specific phenomena which can be captured only if you account for that effect, you have to define additional scalars to keep track of that particular variable. Or if the number of variables, if number of additional scalars becomes equal to the number of variables that you already have, you solve the original equations. That's it. Yeah. But the point to keep in mind is even for such a problem, you might want to actually get solution by this approach and use that as the initial solution, and then add one more layer of detail to actually see the difference between the behavior when Lewis number is 1 and when it is not 1. If you just start with a case where Lewis number is not 1, you may be assigning effects to Lewis number which may be explained only by a simple calculation. So it's a hierarchical approach where you start with the simplest model, and this is the simplest model to start with. Yeah. In fact, one effect of Lewis number not being 1 will be that the behavior of the flames under stretch will become different from what it is when Lewis number is 1, because the rate of transport of mass and rate of transport of heat will be different. The same, if you choose a small control volume and look at the energy balance when Lewis number is 1, Lewis number is not 1, it's possible that under certain conditions there will be loss of energy from the control volume, or there will be gain of energy by the control volume. Other questions? Yeah.
Then how you can calculate Taylor levels so it will become?
Yeah, I will discuss that when I discuss the flamelet model itself. Well, we don't have to actually wait, it is calculated by solving this equation with a reaction mechanism for different values of the scalar dissipation rate, okay. So one configuration which is used to generate these flamelet libraries is what is called the opposed jet configuration, which is a slightly different version of the porous cylinder flame that we saw. The idea is to create an opposing jet of fuel and oxidizer. That is what was done that is what was shown in the porous cylinder case. Another way to create it is by having two jets going in opposite directions. One is issuing fuel, other is issuing oxidizer. This configuration was discussed in one of the earlier lectures. You ensure that the momentums are balanced, so you have a stagnation plane, and the flame is usually on the oxidizer side because of the stoichiometry being much greater than 1, okay. So the structure of the flame in this configuration, see, remember that here the mixture fraction is 0, the mixture fraction is 1. The flow is actually 2-dimensional, but when you see it in the z coordinates, it is 1-dimensional, where the profiles are simply governed by this equation which we just saw. See, and so on. You can write an equation for this may be plus okay. You can solve these equations for a certain reaction scheme for different values of chi, okay. And we saw that when you continue to increase the flow rate of the oxidizer and the fuel, there is a critical flow rate at which the flame will become extinct. So the point of extinction occurs at a critical flow rate and that corresponds to a certain critical value of the scalar dissipation rate, critical value of chi. This is called the chi extinction. Okay. In fact, if you compute the solutions, which I am not discussing in detail, and plot as a function of peak temperature and 1 by chi stoichiometric, you will get a curve like this. Okay. This is the cold branch, this is the hot branch, this is a point of extinction if you okay, this is the point of ignition called the S curve. Okay. I did not go into the details because we will not be using it, I just wanted to give you an overview of what it means, but we have gone into some detail now. Yeah.
If in the equations means that a single fuel or the mixture of fuel?
Here of course I have assumed that I am looking at this reaction. Okay, but you can have multiple reactions. When you have multiple reactions, you have to, your conserved scalar will not be YF, it will instead be the mass fraction or the normalized mass fraction of the carbon element or the oxygen element or hydrogen element. Because even when multiple reactions happen, all reactions put together, the number of elements are conserved, species need not be conserved. Okay. So the way to derive the equation is, instead of starting from, instead of combining the species equation, convert the species equation into element mass fraction equation, which you can do by converting the mass fraction to mole fraction and multiplying by, yeah. Any other questions? Yeah. Okay, so we have gone from the definition of scalar dissipation rate and we have looked at the basic scales of turbulence, and therefore the scalar dissipation rate is nothing but the inverse of the time scale for mixing or simply the rate of mixing. And in most turbulent situations, because of the relationship between the stretch rate or the mixing rate at the Kolmogorov scale to its ratio at the integral scale being proportional to the square root of Reynolds number, and the stretch rate at the integral scale itself being proportional to epsilon by k, the mixing rate can simply be related to the turbulent time scale, okay, which will be k by epsilon. And this connection or this connection between mixing rate and the turbulence parameters is what is used in many turbulent diffusion flame models. Okay. Remember that when you are imagine that you are simulating flow through a practical combustion device using RANS models. Okay. So you need the average reaction rates, and since the reaction rates are an exponential function of temperature, if you simply calculated the reaction rate at the average temperature, it will not be representative of what is actually happening in the system, because you are plugging in the average value into an exponential function. Okay. So if the temperature fluctuates around the average value, there can be a large change in the reaction rate, and this is the fundamental problem with turbulent combustion modeling. Okay. So what is done is that when you identify the limiting phenomena and identify the time scales and the length scales associated with the phenomena, it simplifies the procedure for calculating average reaction rates. Okay. So remember that omega dot is equal to minus is omega dot is actually proportional to the scalar dissipation rate when the phenomena is largely mixing controlled, and therefore if we can get an estimate for the time scale of mixing from simple turbulence parameters, we can get an estimate or we can get an accurate estimate for the reaction rates. I think we will take a break now and come back in 15 minutes and continue with this. Yeah. Thank you.